Hello everyone, today we are going to talk about non-left-orderable surgeries on iterated one-bridge braids. The airspace conjecture states that for an irreducible rational homology three-sphere, it's equivalent that it is an airspace or its fundamental group is not left-orderable or it does not admit taut foliation. The definition of an airspace is that the dimension of the Higa flow homology is minimal, which means it is equals to the size of first homology group. In 2004, Oswald and Double proved that airspaces doesn't admit taut foliations. That is, the condition 1 implies condition 3. Today, our focus is on the non-left orderability, which is we are given airspaces of some form, and we are going to prove that its fundamental group is not left orderable. A group is called left orderable if there exists a total ordering on G such that it is invariant under left multiplication. This total ordering is called left order. A theorem in 1963 states that a countable group is left orderable if and only if it acts on the real line by orientation preserving homeomorphisms without global fixed points, which just means a map low from the group G, or the pi1 of Y, to the homeomorphisms from R to R and strictly increasing, with low of the product of G and H equals to composition of low of G and low of H. And the low of 1 is the identity map on the real line. And there's no real number X, such that X is a fixed point of every low of G. If we have such a map low, then we can recover the left order by the relation that G less than H, if and only if low G of 0 less than low H of 0 as real numbers. One way to construct many airspaces is via dense surgery. And since Higa flow homology works well with dense surgery, we have the theorem that if knot allows a positive dense surgery that produces an airspace, then the set of slopes that produces an airspace is from 2 times genus minus 1 to infinity. A one-bridge braid is a positive braid that is isotopic to a union of an arc gamma and a bridge delta, where gamma transverses to each meridian and the delta is inside a meridianal disk. A theorem of Goodbye proves that for any one-bridge braid, we can represent it by 3 parameters omega t and b in the following formula. But we should be careful that if we represent the one-bridge braid this way, we have to make sure that it is a knot rather than a multi-component link. A theorem in 2018 states that closures of one-bridge braids are airspace knots. That's what we want. Let's take a look at an example of one-bridge braids where omega equal to 7, which means there are 7 strands in these braids. and t equals to 4, there are 4 partial twists here, and b equals to 2, that means that this bridge covers 2 strands here. That's very intuitive. Our results is for iterated one-bridge braids. The definition of iterated one-bridge braids is like the definition of the iterated torus knots, where we just generalize the torus knots to one-bridge braids. They are braids. They are braids that obtained from satellite operations on one-bridge braids, where the pattern knot is one-bridge braid and the companion knot is either a one-bridge braid or an iterated one-bridge braid. We prove that the airspace conjecture holds for airspaces obtained from dense surgery on closures of iterated one-bridge braids. Earlier this year, Chen proves that the airspace conjecture holds for airspaces obtained from dense surgery on twisted torus knots form LMPQ, where Q equals to KP plus or minus 1. This family of knots are 1-1 knots, and they are airspace knots, and we can prove that they are closures of one-bridge braids. The proof is not hard, as we can find their 1-1 diagrams and see they're the same, or we can prove it algebraically using braid words. Our ways of proving the non-left-orderability is that we define a new partial order C here based on the left order, that we say F less than G on the order C if and only if for every H in G. FH is less than GH under the left order. The partial order C, as we define here, is invariant under left multiplication and right multiplication. If this partial order C is trivial, then it's not helpful. So we are going to find a special element K in G such that Law of K is a homomorphism between R without fixed points. Since law of K is a continuous function, it is either pointwisely greater than identity map or pointwisely less than identity map. In the first case, we can prove that K is greater than 1 under order C, and in the second case, K is less than 1 under order C. If we have such an element K, that means C is not trivial. Now we summarize the properties of the positive column of the order C here. The first and the second property guarantees that it's left invariant, left multiplication invariant, and invariant under right multiplication. And the third one is also satisfied by the order C. F to the nth power is positive under order C. That means any conjugation of f to the nth power is positive under left order, then that implies any conjugates of the f is positive under left order, which means f is positive under order C. Now we are going to construct another order here. If we have a subset Sk of G, any subset, we can define a pre-order in that f less than G under order K if and only if f inverse G is in the root closed conjugacy closed submonoid generated by S of K. And this order satisfies that it is invariant under left multiplication and right multiplication, and also a root closed condition for that. And the theorem here is that if every element in Sk represents a map which is pointwisely greater than the identity map, then the partial order C is an extension of the pre-order K. And similarly, if every element represents a map pointwisely less than the identity map, then partial order C is an extension of the inverse of the pre-order K. And under the condition of this theorem, we have that the pre-order K is a partial order. If we can prove that the pre-order is not a partial order, then we get a contradiction. In a summary, when we are giving a group G, first step is to find an element in G, such that for any homeomorphism low from the group G to the homeomorphism group orientation preserving homeomorphism group on the real line, if S is the fixed point of low of K, then S is a global fixed point. And the second step is to define the pre-order K generated by the single element K and prove it is not a partial order, which means we can find an element that is greater than 1, less than 1, and not 1. Then G is not left-orderable. These two steps are equally important, but the proof for the first step is usually shorter than the proof for the second step. I think the second step is where we must use those genus bonds and such. So why are we doing this partial order, this pre-order, instead of just working on the left order, the total order? The reason for that is for the total order, we are going to prove it doesn't exist, and there could be many possibilities along the proof. But if we are given any specific element in this group, then the pre-order is fixed by this element K. So that the computation is less challenging, and we can get meaningful partial results. Now let's look at satellite knot. First, we are going to find one satellite knot gives airspace knots. For cable knots, where the pattern knot is just the torus knot, in 2009 and 2011, they proved that the cable knot is an airspace knot if and only if the companion knot is an airspace knot and the slope is greater or equal to 2g minus 1. And in 2015, the results are generalized to the case where the pattern knot is one bridge braid instead of torus knots. If T over omega is greater than or equal to 2g minus 1, and the K is an airspace knot, then the satellite knot is an airspace knot. Otherwise, it is not an airspace knot. As we are going to prove that the non-left orderability for dense surgeries on iterated one-bridge braids. And we have two steps. The first step is to find an element without fixed point. The second step is to prove this not a partial order. We developed this notation of property D that can transfer fixed points in the previous level in the satellite knot to a fixed point in the next level, and the second condition here is used to transfer the information, the partial order information on the current level to the previous level. And we have such a theorem says if a knot has a property D, then the fundamental group of the manifold obtained by dense surgery on K with slope P over K greater than or equal to 2G minus 1, the tight bond here, is not left orderable. The motivation of the property D is that I saw a definition in 2011 of the decayed knot that was used to prove the non-left orderability for dense surgeries along certain cabled knots. And in their definition, a knot is called R decayed if and only if for any positive coin in the knot group, either mu will represent here mu represents a meridian and lambda represents a longitude. Mu to the p's power times lambda to the q's power are all positive or all negative. And if this is the case, then p mu to the p's power times lambda to the q's power can't be 1. And the same condition here holds. Same conclusion holds here. Now let's compare the property D with the 2G minus 1 decayedness. The first difference is in our definition, the first condition, the fixed point condition, uses the fact that law of mu and the law of lambda share the same fixed point sets. If we have mu to the p's power, lambda to the q's power equal to 1, and P and Q are not zero. While in the Clay-Weston's definition of decayedness, they only use the fact that, say, P, let's say, mu to the P's power times lambda to the Q's power is positive, and then say mu is positive, then they conclude that any mu to the P0's power times lambda to the Q0's power, where P0 over Q0 is greater or equal to P over Q, then it's also positive. So the fixed point condition here, it's really something special we used in the dense surgery. And the second condition, pre-order condition, is an obstruction for left orders with the pre-order generated by two elements, the mu inverse and the mu 2g minus 1 times lambda. It's surprising that we just use those two elements, then we can generate a contradiction for left orders. Since for the first condition, our definition of property D is weaker, and for the second definition, the condition in property is stronger. They don't imply each other in obvious ways. There's still room for equivalence, but that would be an ambitious conjecture. Our result is that non-trivial knots, which are closures of one bridge braids, do have property D, and also that if we have a satellite knot with pattern P being a one bridge braid, and the companion knot is a non-trivial knot with property D, and that T over omega is greater than or equal to 2g minus 1, which is also the tight bond here, then the satellite knot has property D. Combined with the theorem here, we have that the airspaces obtained from dense surgery on iterated one bridge braids has non-left-orderable fundamental groups.